Good morning, everyone, and thank you for joining me today. Obviously, I'm very, very excited to have my very glamorous assistant, Dan, back online today. Welcome back, Dan. We're all really happy to hear that everything went fantastically. And yeah, I hope you enjoy another day of being able to put your feet up while I do the heavy lifting, so to speak. So again, thanks for everyone for joining today. Today will be a continuation of network analysis, and I have good news and I have bad news. The bad news is this morning is going to be quite theory heavy, explaining what the different metrics are that you can look for when you're doing your network analysis and looking at graph theory. But the good news is this afternoon, we're then going to get on and actually do some web-based visualizations. So kind of similar to Folium, something that appears in a web browser and you can make it interactive. So hopefully there is the light at the end of the tunnel once we get through this morning. Just go to the next slide. Obviously, as I say, this morning is all about the theory. So this is about the graph metrics, what we are really looking to understand once we've created or once the algorithms have created the graph for us. And they really help us to understand what is the topological structure of the network and the relationships between the different nodes or vertices or the services, if you like. And don't worry if you don't know what topological means, we'll be covering that shortly. And it really is a core component of network analysis. As much as we would like to think it's just about making something that looks pretty, there's a little bit more to it than that. And it's really important that we're able to kind of understand and interpret these metrics to understand what is actually happening within a system. And then being able to understand these particular insights allows you to communicate to others who may be less technical about what is actually happening there, both at a static point in time, but also looking at changes that may occur over time. So just to go back and just refresh everyone's memory, because obviously last week was a long time ago, just some terminology for us. We have the dots, and they can be known as vertices, vertex, or nodes. They are used interchangeably in the literature. So if you are doing a project that touches on network analysis, just make sure you remember nodes and vertices, same thing, used interchangeably. And these here are the dots identified V1 through V5. And then we have our edges. And these are our lines or links, and these can be identified in two ways. You can either call it, if we look at this one here, edge 1, single nomenclature, or we can think of it as the edge that links V1 to V2. And obviously, whether it's directed or undirected, we'll have a bearing on that as well. And then just to move on from that, we've got edges that are parallel. And so that would be, if we look at E4 and E5, we have those listed there. Now, it's interesting to remember that you can also have parallel edges, which are edges that terminate at the same node. So in that, looking at that, if this was a directed graph going from V1 and V5 down to V2, E1 and E2, they would also be classed as parallel because they have the same terminating node. And that took me a little while to get my head around, so feel free to circle back on that later. We have an edge will become a self loop if you look at this V5. So highlighted in the green here because it starts and ends at the beginning and end. And in real worlds, that would be a patient that would self-refer back to the same particular service. We have our adjacent nodes, and this is any nodes that share a common vertex. So similar to parallel, but this one will be probably more used in undirected graphs. So we can see in this example, an adjacent will be V2, because you've got E1 and E2 share a common vertex. And then just finally, two vertices are adjacent if they're connected by an edge. So V1, V2, they are adjacent because they have E1 going between them. And that is important to bear in mind when you're thinking about how you would walk through a graph. And when I say walk, for example, if we would start at V1, we'd traverse the first edge to get to V2, we'd then go up to V5, we then travel down to V4 and then up to up E5. And again, this is, the walk, so that the route that you're taking through the network based on the connections that actually exist. So just to give you a little bit of a history, I know it was touched on very briefly in the last session, but we have the 7 bridges of Konigsberg problem, and excuse me if I have not pronounced that correctly, and this was a problem that kind of really started graph theory, and back in 1735, Leonhard Euler was kind of tasked with a problem. In this particular city, it was a garden city, there was, 2 main banks, the north and the south, and then there was 2 islands that sat in the middle of the river. And then there was all these bridges between the different parts. And it was quite fashionable for people to kind of go and walk around and, go out in all their finery, kind of like Bridgerton, I'm imagining, going for a walk around and be seen, crossing the bridges and going to see all the different gardens that were available. And what they wanted to know is, was it possible to traverse every place but you only using each bridge once? And it is a form of the traveling salesman problem when you think about it. They've got to get to all these different locations. But just to kind of get your thinking, and this is going to be an individual task, you're not going to be in your peer support groups. I'm now going to give you 5 minutes and just think about how you would represent this problem in graph theory with nodes and edges, so dots and lines. And I want you to be able to tell me after 5 minutes, is it possible to traverse each bridge only once, but make sure you're visiting every different location? All right, so 5 minutes and off we go. And after the 5 minutes, I want people to put their answers into the chat window, just a yes or a no. So there you go, time's up, and I'm very pleased to see that there was a general consensus of no, with or without the aids of boats flying, building more bridges, or bridges falling down. So as we can see on the left, this, how the map looked. But then what Euler was able to do was come up with the graph representation on the right. So the nodes being the particular banks and the edges being the bridges between the different areas. Now, just some observations here, that if the degree of all nodes is odd, then there's no way to traverse only one. So the degree is about the number of edges from each particular node. And each node in this example has a degree of 3. Where's my mouse? So you can see this node has 1, 2, 3 edges. This one, 1, 2, 3. Oh, sorry, 5. Ignore me. Odd numbers. But what Euler was able to do was to discover that it was not possible, given an even number of nodes and an odd number of edges, to have what's called a unique walk, so a way to kind of cross everything just once. It just wasn't possible. But this really gave birth to the problem, of using this type of terminology to kind of abstract real-world problems, to solve them mathematically, to work out, different answers. So kind of moving on from that, it's kind of important to discover, well, what are the different types of graphs that we have available today? Now, remember, graph theory is based in mathematics, and what I call maths heads are a special breed. And so they like to have an answer for everything, and everything has to be very, very precise. And so with that, we have just the main types of graph to identify. We've got our empty graph. And so this has got no edges, it's only got the nodes. Now, the empty graph is not to be confused with the null graph, which just has nothing. There's nothing there at all. So, that's a complete absence. You've got a trivial graph, which we can see here, has just one node, and that's it. There's no edges, nowhere to go. And then we've also got a complete graph. And in this example, the complete graph is when you have all nodes are connected by all edges. So in this example, there's no other connections that it can have. Now, kind of taking this one step further, the different types of graph types that you have available, there's two main types really, and that is undirected. And this is where the direction of travel between two nodes or vertices does not really matter. An example here would be, look at a social network. If John and Jones and Smith are friends, it is what's written there. It doesn't matter which the direction of travel is purely in an undirected graph. You'll see how that may alter in a second. But then if you've got a directed graph, this is where the direction of travel between nodes is important. And if you think about this, think about healthcare. Let's say you wanted to look at a district general hospital. Someone presents an emergency department from there. They could be referred up to orthopedics. They could go here, they could go there, and so on and so forth. And so the direction of travel does matter, and probably quite rare that a patient comes back down to emergency unless there's some kind of big problem. We've then got weighted graphs. And with the weighted graphs, you're then not just saying, well, there's a direction of travel between these two nodes, but you're giving an indication, well, how much is it traversed, or how, for example, how many patients will travel that, how many patients are referred from emergency to cardiology or to orthopedics or whatever it happens to be. And so obviously this is, quite important if we're doing something in health services. You want to see the most commonly tread paths, and then you identify things that aren't commonly used and see, well, why is that and what can we do about that? I should just point out, as well as the names, I'm giving you the nomenclature of how we would use the NetworkX package within Python if you want to instantiate any of these particular graph objects. So you can see you instantiate them by saying nx.graph or digraph, and then you can add your edges. Then we've got the signed graphs. And now this is quite an interesting one. And the best example I found to kind of convey this to everyone was just, if you think about social sciences, and let's say there's a connection between two individuals, but can you describe that connection to be a friendship? So that would be a kind of positively signed, or let's say it's some form of hostility, that would be negatively signed. And again, that can be interesting. There is a link there for anyone who wants to understand more about that. And then you've got a multigraph. And this is where there may be different types of edges or connections between two different nodes. And this, for example, could be based on the type of relationship. Are these two individuals friends? Are they family? Are they co-workers? Or are they a neighbor? And you can see here, there's different colors based on the type of relationship that these people have. So just thinking about some very common graph metrics. We've got the network level. So this is all of the graph, or think about the complete system, the complete ecosystem that we're looking at. Very basically, we would consider the total number of nodes and edges. And this would really give us the base description of a network and its complexity. So as you can imagine, something with 5 nodes and 3 edges is a lot less big and complex than something with 200 nodes and 60 edges. And commonly we refer to anything, a large graph would be something with 200 plus nodes, just to kind of give you an idea of scale. We then have density, and that is the number of links that exist, or number of edges that exist, with respect to the number that could potentially exist. So imagine if something was complete, it was saturated, every node was connected to every other node. And this is kind of on a scale of 0 to 1. So 0 being empty, as opposed to null, and then 1 being complete. So again, this is where we're starting to layer the different metrics and the different terminology that we've seen in the earlier slides. Then also at the network level, we can also consider the average degree. So remember, the degree is the number of edges going out of each node. And so with the average degree, let's say that one node has 5 edges, another has 2, and another one has 6. Well, then you'd sum them all together and divide by 3 to work out the average degree. And then with the network modularity, this is really thinking about the connectedness of the graph. How many nodes are kind of clustered together within close proximity, and have some kind of groupings, and you may have kind of more distinct groupings that exist in different areas. Now, all of these, as I say, are at a system level, looking at holistically, looking at the whole Konigsberg situation. But then we've also got the kind of the common metrics that will be associated at a node level. And so this is thinking, as I say, at the individual node level. And so you've got the degree, as as we talked about with average degree. But this would be slightly different because if you've got a directed graph, you would have to worry about the in degree inwards and the out degree outwards for each of the nodes. And the sum of those together would become the total degree. And this is a good way to understand how well the nodes are connected. Those with a higher degree are connected to more services. And you'll see why that may or may not be a particular problem when we're considering health systems. We then got modularity, as I say, at the node level. And then again, that's how well connected a particular node is in relation to others. So how close together is it to its nearest neighbors, if you like. And then you've got something called eigenvector centrality. And this basically is, what is the connectedness of the node in relation to the whole network? And the best way to think of it is like if you've got a single point and it's, this one particular node, and let's say in primary care, for example, and you've got someone and they seem to be the one that connects all the different services, they're referring people to different specialties or different services. They're the kind of movers and shakers because lots of people go to them and then they also refer them direct to other places. They would have a high centrality because they're in the middle and they're connected and they're kind of keeping everything together. And again, I do apologize because there is quite a bit of theory to go through. So it is a bit heavy on the content, but we will have some frequent breaks, and also you'll get to try and actually do some Python coding to see how to work out these different metrics. And then you'll have these notes to refer back to, but actually the NetworkX documentation is excellent as well. So thinking about some more complex graph metrics, we've got these approximation or heuristic techniques. Now, remember, heuristic being rule of thumb. And the reason that these are important is, as you can imagine, working out these different metrics, if you've got a big, a large graph, 200 plus nodes, it's maybe computationally heavy, so NP hard to actually work out every possible combination to get the metrics. And so some of the things we do at a kind of a high level to get an overall view of, the complexity of the graph is look at the overall connectivity. We then have things called clique detection. And so maybe just looking at the number of cliques. And a clique is where you have a group of nodes which they're all clustered, they're all connected to one another, but they sit distinct to the rest of the graph. And again, I'll touch on that a little bit more with a visual example shortly. And then you've got clustering. And again, these are, groups of nodes that are all appear to be clustered together, but separate from one another. And in health services, usually when you look at clustering, you do tend to find that these nodes or services tend to be clustered together based on the geography. So you may find these services are close to one another physically, as well as how they appear when you draw your network graph. You've then got centrality. And so the measures of centrality available are degree centrality. So which nodes are most highly connected by the number of connections. You've got your eigenvector centrality. And this is otherwise known as a prestige score, because obviously, as I said, these are the ones that are kind of connecting everyone together, the people in the middle that hold it all together, if you like. And then you've got centrality, which is just another variant of eigenvector centrality and calculated slightly differently. Then on the right, we've got our, cliques clustering communities that we need to consider. So this is how well the nodes are, bunched together, if you like. And you can look at the clique community, so how many of those exist. You've got the greedy modularity communities, and this is basically, you kind of walking through the graph and seeing how well each node is connected. You've got these things called isolates. And so this is where you just, you might have a graph, but then you might just have a dot, a node out on its own, and it's it's not interacting with anything else, but it exists. And so then, if you identify these, you've got to ask yourself, well, is there a problem with the data, or should this be happening? Why is this service existing, but it's not interacting with everything else? Should it be? Should it be merged into something else, or should it just not exist altogether? Maybe you need to redefine the parameters of who is using that service and why. Then you've got the link analysis, and this is all about looking at the connections that really exist between the different nodes. And with this, you've got the predictive elements. So when the connections could form and their closeness to others and nearby connections. Then you've got shortest paths. So let's say we've got, again, going back to Euler's example, there was a city with more bridges and more islands to consider. With the shortest path, you just want to see, well, what is, to get from A to B via C, D, and E, what is the shortest way to get there? Because there may be more than one option. And so it's often, you want to find the optimal path between a certain number of points. And then you've also got the similarity measures. Now, with the similarity measures, this is very good if you want to look at a temporal situation. So you want to look at how a system existed 12 months ago, a complete ecosystem, and imagine some changes are being implemented and things, have changed over that time period, and then look again 12 months later, and it's kind of comparing and contrasting, and it's finding out, well, what is the minimum cost of transforming the original to the new, so you can then start to unpick and determine, well, what was the impact of the changes that have made? Are we seeing more referrals, fewer referrals, or what is it that has caused that change? Now, as I said, a lot of information to consider, but the great news is the documentation is very good. So anyone who kind of wants more information or further clarification on what I've said, please feel free to dip in to the NetworkX documentation. And with that, I would actually like to propose a 10-minute break for everyone. Go and get a very strong cup of coffee or tea, because you're about to need it, because as I say, there's going to be lots more theory to come. And so if everyone is okay, we will reconvene at 8 minutes past 10. And hopefully your pub isn't open yet, Dan, so you can't roll back up the hill drunk as a skunk. And even if you do, as long as you keep your microphone off and you're not too disruptive, we won't mind. As we can see, Dan has obviously got his sense of humor back after this procedure. Anyway, I'll see everyone back here at 10:08 and enjoy your hot drink. Thank you. Hello, everyone, and welcome back. Can I just quickly make sure that the you can still see the NetworkX documentation slide on the screen?
Yeah, we can.
Yeah, great, thank you. Cool. So nice, easy one to get us going with these metrics is degree. Now, as I've said before, if it's undirected, it's single, and then if it's a directed graph, you will have in degree and out degree. And as it says here, it refers to the number of edges intersecting a vertex or node. And the thing we look at a system level would be the average, and this can be the average in, the average out, to see as a description of the graph. And then with this, we may take it one step further, and we might start doing some descriptive statistics and go for each node. What is the minimum number of connections? What is the maximum number? Standard deviation in number of connections it has. Or you may even want to plot a histogram so you can see, where the average will fit. And it really is an indicator of system complexity at the nearest neighbor level. And that really means it's referring to those nodes to which it is closest. And then in operational modeling, so if you're thinking about a health service, you may want to understand the number of interfaces that other services are having. And the reason that becomes important, as alluded to earlier, is, if you've got, you imagine you have to deal with 5 different services, but each service you interface with, you communicate with or refer people to, let's say they have a different protocol. Some of them like a paper form, some of them like a hideous form that's built in Microsoft Word that doesn't work. No judge, wink, wink, Dan. Some of them prefer it all to be done via email, and there's no particular form. And all of your staff have to remember, if I'm dealing with this person, I do this. If I'm dealing with this, I do that. And it can get quite complex. And if you send the wrong form to the wrong people, it can just cause lots of problems down the track. And so this is why the degree is something that may be of importance or worth consideration. Can you streamline things? Could you say to them, oh, could we not just have a common referral pathway and get everyone on the same page, just to make life easier for the teams working within the services? And if we wanted to implement this, and all of these slides will show you how to use the NetworkX library for Python, we would just use we've imported NetworkX as nx.degree. The G is the graph object. And if we wanted to get it to focus in on particular bunches, as it's called, or particular areas, you can pass in a list and just specify within that list, which nodes you want it to look at. And also, if there is any weighting to consider that hasn't been added to the graph, you can put that in as well. And then this is going to return a degree, either of a single node or a bunch of nodes or everything, if no end bunch is specified. So relatively straightforward to be able to get that out. And as I say, you'll have a play with these shortly. And I do apologize because I've realized that I had my camera off before. So all of my mad gesticulating to try and convey things has been missed. So your loss. Next, we've got modularity. And again, I think having the image really helps here. So with modularity, again, you're looking at a measure of the structure of the network and how well the structure divides into modules. And so within each of the gray areas on the image, you can see that there's more connections going on there. And then between the gray regions, there are fewer. And as I say, these tend to be, when you look at this in reality, you'll often find you kind of get these clusters will be split by geographic region. That's just the way it works out. And this is often a very good kind of, heuristic or rule of thumb way to look to see if there's any clustering or any communities occurring, just because it can be, as I say, computationally an NP-hard problem. And so, as I say, it's a good first step before you go on to do something more complicated in big graphs. And again, the way that this can be implemented, it's slightly different if you're looking at an undirected versus a directed graph. Would just be nx.modularity_matrix, and then passing in the graph object. Again, if you want to look at specific nodes, you're passing in the list. And again, if they're weighted edges, you can put that information in as well. And if you're looking at a directed graph, then it is nx.directed_modularity_matrix with, again, the same parameters. Again, all of these are covered in documentation. So next, we have the density to consider. And you remember before I said that was the score between 0 and 1. And it really describes the connectedness of the graph in terms of the number of possible connections and the number of actual connections. The application here, really looking at the density, provides us a measure of how well or sparsely connected a system is. As we can see on the right, for A and B, they are completely connected. So every node is connected to every other node by vertices, by edges, but then if we look at the third option, C, there's 3 nodes there, but only 2 vertices. So the top one could actually be connected to the bottom one. And if that was the case, it would have a density of 100 or 1, 1. But in this case, because we've only got 2 of the potential 3 being used, it has a density of 66.7%. And again, quite an easy way to implement this would be to use nx.density, and then you just pass in the graph object. Now, next, this is talking about cliques, which I mentioned earlier. So you've got your whole graph or your whole system, and a clique is a subgraph or a small area of that. And this is where, as you can see with the area highlighted in red, that every node is connected to every other node. There are edges between them all. And in reality, you know, the way it's kind of done computationally is to start removing edges around a node until you get a complete subgraph. And it is one strategy to do what's this thing called community detection and look for clusters that exist. Now, obviously, if you've got a small to medium graph, so less than 200 nodes, it can be useful to identify, you know, highly linked services, and then so you can start looking at, can you streamline referrals or looking at the way they interface with one another. But then as it gets bigger, as you can imagine, it can become very computationally expensive. And when implementing this is where you then need to consider, you know, with the find cliques function, you'd pass that in, you'd kind of capture that within a list, because otherwise if you've got several cliques, you know, it wouldn't be stored in one container or one variable. But then a slightly faster way to work, but if something is a bit bigger, you can just look at the number of cliques. So there's 12 of them, not saying where they are, just the total number, as opposed to looking for and identifying all of them and what the nodes are. So next, we have our clustering coefficients. And this is a useful approach to see if you've got services that are working closely with one another. And so, as it says here, for each node in a graph, the number of actual complete triangle subgraphs is calculated as a fraction of the possible complete triangle subgraphs. And so what that means is you take a node and then you look for triangles off it. So just like we have B, so we've got one node and it's connected to two others, and those two are also connected to one another as well. And so really you're trying to identify the number of these complete triangles that exist. And it is less computationally expensive than other community and clique detection algorithms, and so often used when you've got larger data sets or larger graphs to consider. And really it's used to identify highly connected services that are interfacing with many other services. And again, this is a great way for you to start adding more information to your graph by actually changing the color of the nodes based on, you know, the clustering coefficient or how well that particular node is connected around it. And again, function here would be your nx.clustering, again passing in your graph object G, your nodes if you want to provide that as the list, and then also any weights if they haven't been added to the graph already. So next we've got our eigenvector centrality, and this is very commonly used within L services, and it's really looking at, you know, how nodes are facilitating connections across the network. And I quite like this example here, which I have borrowed off a website called Network of Thrones, which I'll show you shortly, but it's people who've done network analysis based on Game of Thrones and the different series and looking at the interactions between the characters, and they have a good section on how to explain kind of graph theory for dummies. And if we look at this particular graph on the screen here, hopefully it's large enough for everyone, you know, we can see that the most connected, or the, you know, the kind of the most influential two nodes are the green and the red. But if we're asking ourselves, well, which one is more important? You know, it depends. Well, what is the measure of importance? For example, to kind of step out of the health sphere, if we were thinking about trading relationships, well, actually, the green one is more important because it is the only one that can trade with each of these four blue dots. They don't trade with one another. So trading wise, they're quite influential. But then, if we, because, looking at the red one, let's say we were considering politics, influence of politics, direct connections, the influence you have on others. The red dot, looking at the connections it has with the other four here, that would be more important. And this is kind of implemented, again, in NetworkX using eigenvector centrality. Now, this is an approximation method. And so the reason we specify the maximum iterations, because it'll look once, it'll do it again, it'll do it. So because it's so computationally heavy, it will kind of keep going until it's either reached a point where it realizes there'll be no further improvement, or its budget of iterations has been extended or expended, I should say. And again, it can be very interesting. You're looking in the mental health sphere, and you want to see, well, who's at the center, who's connecting people between the different services, who's receiving the referrals, farming them out, so on and so forth, because obviously you need to make sure that those services, if they're kind of holding the whole system together, that they have adequate resources and training, and they have what they need to be that center point or that pivotal point that they have become. Now, if you imagine, looking at, I previously talked about looking at a district general hospital, people walk in through the emergency department and where they could go. Imagine how this could look looking at primary care. Look at all the different connections that primary care GPs can be referring to places. This could be quite an interesting one to see how it all works in a local area. Where are they going? Is the consistency between different GPs within the same practice even? So there's quite a lot that you can unpick from here. Then you'll remember we have those isolates. Now these are kind of nodes that sit out on their own. They're not connected to anything else. And then when it's not connected, you need to investigate, well, is that right? Should they be interacting with other services? Or that's fine, maybe they can be removed from this particular piece of analysis because they actually interface with other services, so that's not a particular problem. And so there's two things that you can do here. You can either look at the number of isolates, and that will just return an integer. Sorry, the isolates, and it will tell you, well, that'll give you the identification, the ID of these nodes that are sitting on their own, or the number of isolates. And again, that's just an integer symbol 6. So you know how many there are. Then moving on, and hopefully not too many of you wish you had gone to the pub with Dan and you're able to keep up. We have something called link analysis. And this is based on something called PageRank, which was kind of developed by the guys at Google. And this was a way of, I believe, correct me if I'm wrong, developed as a way to rank web pages by looking at the structure of the incoming links, or structure and the quality, I should say, of the incoming links. That being, if you've got a web page, let's say, and it's being referred to by, say, BBC News and Sky News and CNBC News in the United States, and you get lots of traffic coming through, and because they're good, reputable sources of information, I know that's politically motivated statements, you say, oh, that's great, as opposed to, the search, when that's indexed, you may find that particular web page will feature higher up the Google results, because you go, well, it's well connected and it's kind of linked by reputable sources, as opposed to some website that's only referred to or linked to from blogs, or some random people just blogging about their daily lives. Is that probably as relevant, as important? And maybe not so much. And then I'm just wondering why a link to Alcoholics Anonymous has been put on the screen. Maybe I missed something there. But really, this can be used to kind of build a probabilistic network. So you can see what's the chance of someone in service A is going to be referred to service B or C or D. And then it's best used with weighted directed graphs. And so there's a couple of parameters or arguments here that you may not have seen before. So to implement it, it's just nx.pageRank, again, passing in the graph object. kind of obvious. Now, the tolerance, the toll, which is the final one, and alpha, these are the amount of change that is tolerable between the different iterations. Again, it's one of those things, it has a budget, it's going to try in this terms 100 times, and then once it gets to a point where the change isn't so great, it goes, well, that's it, or it expends its budget of 100 iterations. And again, you can set those if you choose to, and again, more in the documentation about those if you're interested. Next, we have the shortest paths. And if you remember, if you've got all these bridges connecting all different areas and you want to get from one place to another, well, what will be the shortest route to do that? And so this is the path in finding pathfinding, is a common task in network analysis that enables you to know how distant one node is from another, how many jumps to get from there to there. And the shortest path algorithm is really useful in understanding how services are separated by other intermediary services and determining the common pathways. And if you think about it, if there is a common pathway that is kind of the optimal way for people to be referred, or should that not be adhered to on every step instead of referring people to places that somewhere else and somewhere else before they get there, because that's just wasting time, wasting resources. It can be good to identify those and then start looking at exception analysis. Well, why aren't people being referred to those particular ways? And yeah, as I say, it's a great way of identifying unnecessary referrals. And so to do this, there's two different implementations, and you've got shortest path and then has path. So one of them is just going to return a Boolean, the second one. And you've seen here, we've got different methods available at our disposal, and they can be passed in as an argument. So you can have a random walk, which is quite computationally expensive. And then there's a disgista. Again, apologies for the pronunciation this morning. Again, more information available about those in the documentation. And when you have a play with some Game of Thrones data shortly, I would encourage you to start having a look at documentation, seeing what else is available, and start playing around and see what the differences between the different methods are. And so next, which is, say, last but not least, looking at the similarity measures. And again, this is looking at the changes that may occur in a system over time. So it was like this, it's now like that. Well, what changes have occurred? And so what it's trying to do is look at the minimum costs to change from one structure to another. And it's really used when you're comparing systems over time. The similarity measures are to provide you a single function that gives you, the information to say the changes that have occurred, and the different ways that they can be implemented are looking at the graph edit distances, passing in graph 1 12 months ago versus graph 2 graph now. But it could be, as I say, multiple temporal points, 12 months ago, 6 months ago, now, so on and so forth. Then you've also got optimal edit paths and optimize edit paths. And again, you can see what they are passing in and passing out there. So hopefully this is just kind of giving you a whistle-stop tour to the types of analysis that you are able to do when you're performing network analysis, and also maybe kind of illustrated some more examples of why you would even want to do network analysis, because I know that was one of the questions last week in the chat. Hopefully you can now see some of the applicability. It's really about service identification, refinement of referral pathways, ensuring the correct utilization, rationalizing the number of interfaces and way that people are communicating with each other, just to kind of make it as easy as possible, as streamlined as possible, not only for patient experience, which is obviously the most important, but also to ensure cost efficiency. You're not wasting resources and overmanning services that where processes could be streamlined, and you could reduce administrative staff in favor of using more clinical staff to obviously have a higher throughput of services. So we're just at 25 past 10, and next thing is we have got and the task. Now, for this task, you can either use the environments that we created last week, or I have put a link to a Binder Hub environment. So with this, and I'm just going to open my Google window just to show you what's available. So within the within the exercise tab, is it? Sorry, yeah, the exercise tab, there's a single Jupyter Notebook file. And within this, we've then got the library imports I've done for you. You've then got this function to create a graph. Now, hopefully you will remember from last week when we had a play at creating a very simple graph. This is the same code, but just for anyone who wasn't here, we will have, you instantiate a graph object, so nx.graph. You will then get your ID list by pulling in the node data frame and just getting the ID column, so the list of IDs. So these are just unique identifiers, indexes, and you're going to pass that to a list. You're then going to turn that list into, you're then going to get the labels from that. So you'll pull out the node data label, put that into a data frame, and then you're going to turn that into a dictionary, as we saw last time. Then we create our node tuples, and this is using the zip function. So it'll alternate between the ID from the ID list and then the description, and then so on and so forth, so on and so forth. And then we'll get our edge tuples, so looking at our sources and our targets, so origin, destination, pull them out as two separate lists. We will then pull out our weights, because we'll know those as well, turn that into a dictionary, and then create our edge tuples, and then add the nodes and the edges to the empty graph object that we created. We'll then read in the data of interest, and we'll create our graph object using that function above. And then down here, for as a starting point, obviously, I've given you season 1, nodes and edges. But if we go back a level and look at data, we've also got season 2, nodes and edges to have a look at as well. So most of the different metrics I have discussed have already been pre-populated for you. So you may want to call it G1 instead of just G, and then do the same for the season 2 data. And basically, I'm going to give you all an hour. And in that hour, I would like you to work in your peer support groups, go through and have a look at all these different metrics, have a look at the documentation, see what else is available, any other arguments that you can add in there. And then at the end of that, I'm going to get everyone back together. I'm going to spend a little bit of time just coming up with some, I want people to present back some metrics that they have found, something that's just some insights that they have gleaned by running these different metrics on the 2 different series of Game of Thrones. As I mentioned, the documentation is available, and there's a link for that in the slides. And I shall just put that into the chat window now. And then there's also this website, Network of Thrones. And anyone who wants more information, feel free to have a look at this primer of network analysis. But again, this is all about the different network graphs that are being produced based on the different series of the TV show. Again, I'll put that into the chat window. And this afternoon, we'll actually be making interactive graphs ourselves based on the data from the series. So if everyone is all right, I will open the peer support groups, give everyone an opportunity to say hello to each other. Dan and I will be floating around, so if there's any questions, please let me know. But other than that, we'll aim to be back together at 11:30, and then just be prepared for the Wheel of Fortune, the Wheel of Names, just because I'll be asking some groups just to share some of the insights that they have gleaned from this analysis. Okie dokie. Hello and welcome back, everyone. I wonder how all the other groups got on. Unfortunately, I didn't get around to everyone. I think instead of using the Wheel of Fortune to select a group, I wonder if there's any groups that have anything they want to volunteer. And I do apologise if my knowledge of this subject matter is probably not what it should be. I haven't inherited it from someone else, and I've realised the holes in my knowledge by spending a bit of time with one of the groups. So as I say, is there anyone who feels brave enough to share any insights, any Game of Thrones nuts who realise, found or discovered something that they didn't already know about the series? And or anyone who's willing to put anything in the chat window either. All right, well, if not, I appreciate we've still got a bit of time remaining. And so what I thought could be good practice for everyone, given that we're still got not a lot of time, but still a little bit of time for everyone to come up with their project ideas and come up with their project pictures. But working in, again, your peer support group, so feel free if you want to continue on any of the analysis you were just doing, especially if you may want to filter the graphs at all and come up with smaller ones. But really, for the next kind of 50 odd minutes, work in the groups, your peer support groups, and think about how you may be able to use network analysis for any real world problems, not necessarily for your project, but just any problem in the world that think that you could potentially apply this to. What metrics could you think of would potentially be interesting, or what would you hope to uncover from performing that type of analysis? And if it is something that you're thinking for your work or your project, or as I say, maybe not a project, but something that could be done within the area that you work in, how you would involve, if it's health services, how you would involve the public patient engagement, because it's obviously very, very important. And I do fear from hearing some of the conversations that maybe not everyone sees how it's totally applicable. And it really, really does have to be a core element for any type of project that goes forward in the health services area. So with that in mind, if we meet back at 12:25, just for a final 5 minutes recap before we finish for lunch. This afternoon will be very, very different. I'll be talking to you about making web-based apps using Dash Sitescape. And so lots more practicality, less theory to consider, and you'll be making something quite visually attractive. So look forward to seeing you all at 12:25. And again, I'll try and float around the groups and answer any questions that I can. And again, if you can just remember what group number or room number you were in, that would be great. So hello, everyone, and welcome back. I hope that has given you an opportunity just to discuss some potential project ideas with your teammates, group mates. One thing I've said to a couple of groups now, if anyone is, they've got an idea for a project and maybe they might be struggling to think how they would get, involve your public patients. One thing to think about is, once you've planned your analysis of what the project might look like, actually go and speak to members of the public right at the get-go. They're probably going to ask I hate using the word naive, but somewhat naive questions of, well, why? Why are you doing that? Why are you doing that? And so kind of answering that with someone who may not know the intricacies of the service you're analyzing, or the kind of the insights you're hoping to uncover, may help you to better define it, put a slightly different angle on the analysis. Or they may ask a question that you possibly may not have considered, that you may not feel as important to you, but it may be important to a patient. And then obviously, at the other end of the spectrum, once the project is completed, talking to patients then and describing the results to them, again, in language that they're going to understand, and as well as concepts they'll understand. They'll want to understand why you did it in the first place. But again, if you've asked the questions at the beginning, that will help filter through and kind of make sure that you're going to meet the requirements at the other end of the analysis. Anyway, if anyone has any ideas for projects, please put them in the project forum Slack channel. Great place to kind of share and cross-pollinate, because you may read an idea that someone else has. Oh, I could do that and do this instead. So it would be of use. Anyway, we'll break now for lunch. As always, I will keep this Zoom window open, but you can rejoin when we restart at 1:30. And this afternoon, we will be looking at graph visualizations, a tiny bit of theory about them, but then we'll actually get into creating some visualizations using both the NetworkX library and Plotly's Dash Cytoscape. If you haven't already, please try and get the environment working before you come to this afternoon. And once we start this afternoon, I will just show you very quickly right at the beginning how to make sure that you're using the correct environment and that everything is working in Spider, because it is a little different to what we've done previously. Ultimately, we'll be starting a little web server on our machines in the console, and then we'll get a URL or a web address which we'll visit in a web browser, and that is going to be how we interact with the graphs that we produce this afternoon. So a little bit different to Folium, which relied on Jupyter Notebooks, but hopefully all relatively straightforward, and it has been tested on every operating system. Just if anyone's using Miniconda with POP, could be potentially a problem. Anaconda is better, but hopefully no one else is. So all that being said, I will leave you to enjoy lunch, and I will see you all back at 1:30 this afternoon. Thank you very much.